Let's talk about the invisible technologies that pretty much run our entire modern world. Things like wireless communication, RF systems, and radar. These aren't just siloed away in one industry. They're actually the universal pulse connecting everything, from satellites way up in space to the very ground beneath our feet. So here's a question for you. What could a satellite whipping around in orbit possibly have in common with a tiny sensor buried in a farm field? I mean, they seem like they're from completely different worlds, right? But believe it or not, they share a surprisingly common technological heartbeat, and we're going to break down exactly how that's possible. So here's our game plan. First, we're going to decode the core technologies that make everything tick. Then we'll see them in action, from the sky all the way down to the sea. And finally, we'll pull back the curtain on the universal toolkit that ties it all together and show you how all these different fields really speak a common engineering language. All right, first things first, we have to get a handle on the fundamental building blocks. To really connect that satellite to that soil sensor, you need to understand the four key technologies they both, and so many other things, completely rely on. Everything starts here with wireless communication. It's basically the art of moving data through the air without any cables. Simple as that. This is the bedrock for everything else we're about to talk about. So if wireless communication is the what, then radio frequency, or RF systems, well, that's the how. This is the actual hardware, the engines that make it all happen. We're talking antennas, amplifiers, and all the nitty-gritty engineering that goes into designing systems that can send and receive those signals efficiently. Next up, we've got radar and sensing. Just think of this as the system's eyes and ears. It's so cool how it works. It sends out a radio wave, and then it just listens for the echo. And based on that echo, it can figure out what's out there, how far away it is, and even how fast it's moving. And finally, you've got the brains of the whole operation, signal processing. See, the raw data you get from wireless and radar systems, it's messy, it's full of noise. Signal processing is that absolutely crucial step of cleaning it all up, filtering out the junk, and pulling out the useful information we actually care about. Okay, so we've got our four building blocks. Now, let's see what happens when we put them to work in some of the most demanding environments you can possibly imagine, pushing the absolute limits of distance and speed way up in the sky and out in deep space. Up in aerospace, these technologies are everything. They're what lets satellites beam internet down to us across the globe, what allows remote sensing to monitor things like deforestation or melting ice caps, and they power the GPS in your phone that, let's be honest, you probably use every single day. But out there, the single biggest engineering challenge is just distance. A signal traveling from a satellite that's millions of miles away becomes incredibly faint by the time it gets here. So the core mission for aerospace engineers is to design receivers that are sensitive enough to pick up and decode these microscopic whispers of energy from all the noise of space. Now, bringing it a little closer to Earth, in airborne and defense systems, the focus shifts to speed and security. Here, these same core technologies are absolutely crucial for detecting other aircraft with radar, for creating encrypted communication links that can't be jammed, and for tracking fast-moving objects in real time. The challenge here is just pure physics. When an object is moving at incredible speeds, the radar signal that bounces off it actually changes frequency. You might have heard of it, it's the Doppler effect. That means the signal processing has to be lightning fast and super intelligent to compensate for that shift, making sure the system can maintain a perfect track on the target. Okay, so from the high-speed, high-stakes world of the sky, let's pivot and come back down to Earth. We're going to look at applications on land and at sea. And down here, the engineering problems are less about pure speed and more about dealing with tricky environmental complexity and just enormous scale. If you're on a ship, you need these systems for everything. Detecting other vessels, navigation, communication, but the ocean itself creates a really unique problem. Radio waves actually bounce off the surface of the water, creating all these extra echoes that can totally confuse a receiver. This is called multipath, and engineers have to design some seriously sophisticated signal processing to figure out which signal is the real one. Drones are a perfect example of engineering trade-offs. Think about it. They need a constant wireless link for remote control and for streaming video. Plus, they have onboard sensors to avoid obstacles. And the biggest catch? All of this intense, real-time processing has to be done on a tiny device with a very, very limited battery. It is a constant balancing act between performance and power. Now, this same tech is also quietly making its way into healthcare, in things like wearable devices that monitor your vitals, or in remote systems for patient care at home. But in this field, the #1 engineering challenge completely shifts. It's all about absolute extreme accuracy and reliability, because when you're talking about health, patient safety is everything. And remember that sensor in the farm field? Well, now we face the challenge of scale. In smart farming, you might have sensors monitoring soil conditions across thousands of acres, while your automated machinery needs rock-solid communication. So the main problem for engineers here is designing a network that can provide reliable connectivity and sensing over these huge, often remote areas. So we've journeyed from a satellite in deep space to a sensor in a farm field, and we've looked at jets, ships, and medical devices along the way. It's been a ride, but now let's pull it all together and uncover the common thread that connects every single one of them. So what is it? What's the common thread? What is the one fundamental principle that links a fighter jet's radar to a patient's heart monitor? And this is the answer. This is the universal toolkit. Just take a look. Wireless communication and RF systems, they're used in all of these domains. And signal processing, that's the brain behind every single one. The specific application changes, the environment changes, the challenges change, but the core tools from our engineering toolkit, they stay exactly the same. And that realization brings us to our final and maybe the most powerful point. This shared foundation of technology, it acts as a kind of common language for engineers working in completely different industries. This right here is the main takeaway of our whole journey. The core technologies are universal. The application, whether you're tracking a target or monitoring a crop, that part changes. But the fundamental engineering principles you use to build that system, they stay constant. This quote really just captures the essence of it all. The same engineering concepts power systems across defense, healthcare, drones, and agriculture. It really shows you the incredible interconnectedness of modern technology. And what that means is, an expert in one of these fields has the foundational knowledge to innovate in any of the others. And all of this leaves us with one final, pretty exciting question. We've seen this toolkit take us from the farthest reaches of space to inside our own bodies. So as these fundamental tools, wireless, RF, radar, and signal processing, get even more powerful, more efficient, and more intelligent, what do you think this universal toolkit is going to build next?